So the goal of this video is in fact to establish a mathematical model describing enzyme kinetics. One of these equations that was developed by Michaelis and Manton, two scientists. If we look at the step of the reaction, the enzyme first reacts with a substrate to form an enzyme-substrate complex. This reversible reaction has constant rates, which are K1 for the forward and K-1 for the reverse. Then the substrate on the enzyme is converted into a product, and we have a release of the product plus the free enzyme. This reaction is also reversible with a rate constant K2 and K-2.
What about the last step in the model? Is that reversible as well?
Well, yes, this second step of the reaction is reversible. However, you have a very good point, because our study of kinetics is during the early phases of the reaction. At that stage, there is a very, very low concentration of product. So we can consider that the reverse reaction, the one with the rate constant K-2, is negligible. And from now on, what we will do is that we will ignore this reverse reaction and consider that the second step in our reaction is irreversible. Our first task is to combine the three rate constants, K1, K2, K-1, and create a single constant, the Michaelis and Manton constant, or Km. So let's see what happens when we first mix the enzyme and the substrate. In the first few microseconds, the concentration of enzyme substrate builds up. That is what we call the pre-steady state. Then we enter steady state, where the concentration of the enzyme substrate complex is constant. We will study the kinetics of enzyme in steady state. The first thing that we have to do is in fact to determine the rate of formation of the enzyme substrate complex. This rate is in fact the product of the rate constant, here K1, times the concentration of the starting material, here the concentration of substrate and the concentration of enzyme. So what we have is V1, the velocity of formation of the enzyme substrate complex, equals K1 times E times S. The second thing that we have to determine is in fact the determination of the rate of the dissociation of the enzyme substrate complex. And this complex can dissociate in two different ways. We can have production of enzyme plus product, or we can have the reverse reaction where the enzyme dissociates from the substrate. So the rate of the degradation of the enzyme substrate complex is in fact the sum of K-1 times the concentration of the enzyme substrate complex and K2 times the concentration of the enzyme substrate complex. Now we have determined the rate of the formation of the enzyme substrate complex and the rate of the dissociation of the enzyme substrate complex. We are at steady state. That means that these two rates are equal because the concentration of the enzyme substrate complex is constant. So we can determine an equation which indicates that K1 times the concentration of enzyme times the concentration of substrate equals the concentration of enzyme substrate times K-1 plus K2. If we rearrange this equation, putting all the concentration on one side and all the rate constant on the other side, we get Km, which is equal to the concentration of E times the concentration of S divided by the concentration of the enzyme substrate complex. That is the Michaelis and Manton constant. What is the meaning of Km? Well, if we have a high Km, that means, based on our equation, that the concentration of enzyme substrate is low, which suggests that the enzyme has a very low affinity for the substrate. Now, if Km is low, that means that there is very little enzyme that is free, and the concentration of the enzyme substrate complex is high, which suggests that under this condition, the enzyme has a high affinity for its substrate. However, it's very important to note that this correlation between high and low affinity of the enzyme for its substrate and high and low Km is true in only one condition. If the second step of our reaction, the conversion of ES into P plus E, is the rate-limiting step of the reaction. That is, K2 is very small compared to the other rate constant. In this case, Km is proportional to the K minus 1 over K1 ratio, and that indicates the affinity of the enzyme for the substrate. So this correlation is only true in very specific conditions. The next task is in fact to derive a more useful equation for Km. If we look at our equation right now, we have terms that are very difficult to determine. We know how much total enzyme we added in the reaction, but it's very difficult to determine the concentration of free enzyme, E, and the concentration of the enzyme substrate complex, ES. What we know is that the total concentration of enzyme is the sum of the concentration of free enzyme and the concentration of enzyme substrate complex. So we have a new equation, and we can, in our equation for Km, we can replace E, the concentration of free enzyme, by the concentration of total enzyme minus the concentration of enzyme substrate complex. If we do that and rearrange the equation, what we will get is Km equals the concentration of total enzyme divided by the concentration of enzyme substrate minus 1 times S. Now our next task is to eliminate the concentration of enzyme substrate complex, the other term that is very hard to determine. How can we do that? We have to go back to our equations about the velocity of the reaction. If you remember, V0 equals K2 times the concentration of enzyme substrate complex. Now, when we have a very high concentration of substrate, the reaction reached maximum velocity. And at that point, all the enzyme is associated with the substrate into the enzyme substrate complex. So the total concentration of enzyme becomes equal to the concentration of enzyme substrate complex. We can say that Vmax, the maximum velocity, equals K2 times the total concentration of enzyme. Now we have an equation that gives us V0 and an equation that gives us Vmax. We can determine the ratio Vmax over V0, which is the total concentration of enzyme over the concentration of enzyme substrate complex. This ratio appears in our equation for Km. So we can replace the ratio ET over ES by Vmax over V0. And when we do this rearrangement, this replacement in the equation, we get Km equals Vmax over V0 minus 1 times the concentration of S. So we have now achieved our goal. If you take a closer look at the equation, we have two variables, V0 and the concentration of substrate. And we have constant terms, Km and Vmax. We have eliminated all the terms that are hard to determine. Now, if we continue to rearrange this equation, we can express V0 as a function of the concentration of S. What we have as now our equation is V0 equals Vmax times concentration of S divided by Km plus the concentration of S. This equation is the Michaelis and Menten equation. Now, this is an equation that is graphically represented by a hyperbolic curve. And do you remember when we plot the experimental values of V0s as a function of the concentration of S, we obtained an hyperbolic curve. So in fact, the Michaelis and Menten equation fits the hyperbolic curve that was determined experimentally. What can we predict from the Michaelis and Menten equation? Well, we can, for example, consider that the concentration of substrate is very low. So low that it's negligible compared to Km. In this case, the Michaelis and Menten equation becomes V0 equals Vmax over Km times S, which means that under this condition, the velocity of the reaction is directly proportional to the concentration of substrate. This is not very good for a cell. In a cell where you have a very low concentration of substrate, then the reaction is very sensitive to any changes in the concentration of substrate. However, the enzyme will never reach its maximum velocity. So the enzyme will not work at its full potential. If we take the opposite example, we have a very high concentration of substrate, much higher than Km. Now, Km plus substrate in the Michaelis and Menten equation becomes equivalent to the concentration of S. In this case, V0 will be equal to Vmax. Is that better for the cell? Not at all. Because in this condition, the cell cannot fine-tune the activity of the enzyme. The enzyme will always work at its maximum capacity, and it will be a wasteful degradation of substrate even when the product of the reaction is not needed. We can take an intermediate example where the concentration of the substrate is very close to Km. So let's say that it's equal to Km. Under this condition, Michaelis and Menten equation becomes V0 equals Vmax over 2. This is an optimum condition for the cell because the enzyme can both be sensitive to changes in the concentration of substrate, but can also reach its maximum velocity. And this also gives us a new definition for Km. You can see now that Km is the concentration of substrate needed to reach half of maximum velocity. So in this video, we covered a lot of information about kinetics. If you need to go over the detailed derivation of the equation, you should check the kinetics equation document that is on the course website.